In this video, we're going to learn about calorimetry. Now, calorimetry involves both heat and temperature, so before going any further, it's important to understand the difference between them. Heat is defined as thermal kinetic energy, and this heat has units of joules or calories. Calorie is the non-scientific SI unit. The SI unit is the joule. Temperature is an average kinetic energy. So the average kinetic energy is measured in degrees Celsius or kelvins. So we could say that something an object has a certain temperature, but also within that object, there's a certain amount of kinetic energy. And when we compare, let's say we have a small piece of metal that's very hot, it's going to have a certain temperature. Well, a large piece of metal may have exactly the same temperature, but that large piece of metal has much more heat trapped within it. So there's a good distinguishing factor between those two. So next, let's consider if we're going to be determining the heat required to make something warmer. Let's take, for example, a bit of water that we've put on the stovetop to heat up. What factors affect the amount of heat required to heat up the water? Well, one thing is the mass. How much water is being heated up. A little bit of water doesn't require much heat to raise the temperature. More water does. So mass is going to matter. Also, how much you're changing the temperature. Of course, if you're only changing the temperature, raising it by 5 degrees, it doesn't take much heat. But if you're raising it by 20 degrees, it takes much more heat. And then there's also what the substance is. So I've been talking about water, but if we used, for example, a piece of metal, that would have a certain propensity to have its temperature changed, and water would be different. Every substance has its own ability to have its temperature changed. So we come to this equation based on those previous factors. We've got Q is equal to mc delta T. Delta T is just changed to T2 minus T1. What we have here is that Q, the heat required for a change to occur, is equal to the mass of the object that you're heating times the specific heat of that object times the final temperature minus the initial temperature of that object. Of course, that's in parentheses. So you do that first. Now, heat is measured in joules. Mass is measured in grams. The temperatures, we can say kelvins, or we could also say degrees Celsius. Either is fine. But the specific heat, what is specific heat? This is a property that it's an intensive property of a substance. And this is where we're factoring in, again, that some objects may be a little bit easier to change the temperature of just based on the material that they are. Gram per gram, a gram of aluminum is going to be much easier to change the temperature of than a gram of water. So specific heat has units of joules required to raise a gram a degree Celsius. So the units are joules per gram degree Celsius or degree Kelvin. So if you're doing a calorimetry experiment, what you're going to do is you're going to see the amount of energy released in some kind of process. For example, if I have something that I'm burning, what I can do is I can initially light it on fire, and now from this point onward, all of that fire, all of that heat that is being released by this burning object is going to be dissipated, we're assuming that it's going to go into the water. And if we have a thermometer with an initial temperature and we know the mass of the water that's being heated, we can say that the mass of water times the specific heat of water times the change in temperature of the water is going to be equal to the heat absorbed by the water, which is also equal to the heat that is dissipated as there's the burning of whatever the object is. Over here, we have another type of calorimetry setup. So there can be, if you have, for example, some water and you are conducting a reaction in it, when you add something in that causes the reaction to occur and then immediately cover the coffee cup cup calorimeter that this is, you can see that there's going to be an initial temperature, and the temperature will rise as heat is released by the reaction mixture. Once it reaches some kind of maximum, then you know you've taken in all of the heat that could be accounted for, and you can again use Q equals mc delta T for that. So let's solve a problem. We're going to burn a Cheeto beneath a beaker containing 50 grams of water. I'm going to write that over here. The mass of water is 50.00 grams. We have an initial temperature of 23.12 degrees Celsius. That's Ti, is equal to 23.12 degrees Celsius. Now, our final temperature is going to be 38.74 degrees Celsius. So that's 38.74 degrees Celsius. And our specific heat of water is equal to 4.18 joules per gram degree Celsius. So if we were to try to solve this problem, we're looking for the Q, apparently, how many joules of energy were released. So that's what we're solving for. So we need to use our formula, Q equals mc delta T, which is Tf minus Ti. And that means that Q is equal to the 50.00 grams times the 4.18. Sorry about my laggy stylus here. 4.18 joules per gram degree Celsius times the final temperature of 38.74 degrees Celsius minus the initial temperature of 23.12 degrees Celsius. And when we calculate that, that brings us to Q is equal to 3,264.58 joules. Sorry, there we go. Now let's make sure that we have the right number of sig figs. What I'm seeing here is our specific heat of water actually is going to be our limiting factor here with 3 sig figs. So I need to make this 3,260 joules, which, okay, since we're talking about burning a Cheeto, it's food, why don't we put this into terms that you guys are more familiar with, calories, right? You look at nutritional information in a bag of Cheetos and you don't see joules as your energy, you see calories. Well, I'm also going to convert from joules to calories. I got 3,200, and I'm actually going to keep it at the 64.58 joules. And I'm going to convert knowing that 1 calorie is equal to 4.184 joules. And what I get is that we have, with the right number of sig figs, 781 calories. Wait a minute. One Cheeto releases 781 calories? There seems to be a problem here. Actually, what you read on nutritional information, it's not calories, it's kilocalories. It's just listed as calories. A kilocalorie is, of course, 1,000 calories. And a kilocalorie is otherwise known as a food calorie. Well, so I need to do another conversion here. 781 calories times 1 1 kilocalorie, over 1,000 regular calories. Again, not what you normally would see on a nutritional information label. We actually end up having 0.781 kilocalories, which I think for you guys would probably be a little bit more believable that there is a little bit less than 1 calorie per very small Cheeto. Anyway, so that is that. That's all for this. In the next video, we'll talk about heat transfer. Hope this video has been helpful. Let me know if you have any questions or comments in the comment section below. Thanks for watching.